My name is Jonathan. I'm the manufacturing manager at Alba Orbital. My goal here, I've been here coming up on 1 year now. My main mission, I think, at the company is to increase our production rate. And you may be thinking, well, we've launched some of the largest number of PocketQubes, and how many more are we going to launch? And I'd love to know that number. I don't think we have it quite yet. This talk yesterday, he did allude to the fact that we are, right now we're currently running at 30 to 40 meter GSD. And we want to get that down to 5 or sub 5 meter. What that'll do, we'll also reduce our field of view, which will mean that we'll need more passes to get more images. In order to cover the entire Earth, we could need many, many more satellites. So we're going to begin to see how many we're going to need, and it'll be my responsibility to build them. Where's my experience to help out in this coming from? Prior to coming to Alba, I worked at SpaceX for 7 years, from 2012 to 2019. I had a variety of different projects and programs that I worked on while I was there, predominantly around increasing rate of production on Falcon and Dragon specifically. And you may wonder, how does one get a job like that? And so my experience prior to that brought me to SpaceX was from the automotive manufacturing industry. I spent a number of years working on assembly lines and producing improvements in rate of production in the automotive industry back in America. Interestingly enough, the vice president of manufacturing at SpaceX at the time that I was working there came from a similar role of VP of manufacturing here in the UK. And so it is possible to find alternate ways into the space industry, even from here in the UK over into America. Okay, so I don't want to talk too much about automotive, though. Right now, we want to focus on PocketQubes. We want to focus on space. Even SpaceX is a little bit stretch here, right? How could these be more different? So I'm gonna set that aside. If you want to do a deeper dive into automotive and where some of the background behind what I'm going to talk about is, you can do some searches on lean manufacturing, Six Sigma, Toyota manufacturing system, a Toyota management system, things like that. There's a lot of material out there, how the automotive industry has innovated and brought about rapid increases in production of a complex product like a car, similar to a large sat, and how you break that production up into smaller and smaller elements in order to get a high rate of production. And of course, we aren't necessarily going to get to the rate that an automotive plant might see. But as we go through my slides here, you're going to see how this becomes relevant from SpaceX. And I'm going to connect that to where PocketQubes could go and some of the benefits we can see through PocketQubes. Okay, so right here, we've got Starship. I'm not going to talk about that too much either, but I do want to throw a challenge out here to folks in the room that I haven't heard a lot of people talk about this particular topic the last couple of days. Certainly a lot of great stuff being talked about, but I don't think it's going to be very long before we start seeing commercial payloads launched into orbit with Starship. That seems to be the pattern that SpaceX can achieve something by proving over and over, spending lots of money on it, lots of iterations to get a goal. Now, obviously, Starship is taking a little bit longer than they planned, but once that starts happening and they start putting payloads into orbit, I don't think it's going to be very long before they start sending stuff to the moon. SpaceX has seemed to pivot to the moon for some reason. And when they start sending payloads there, there's going to be an opportunity for rideshare to the moon. Again, perhaps a few years more, maybe 6 years. That's not that far away. We might have an opportunity to send PocketQubes to the moon. So I think that's my challenge to throw out there. Think about that. Think about payloads that can go. Alba would love to be the first deployer of a PocketQube into lunar orbit. And here I've got the comparison with a 1P over here. Now you may say, oh, well, that's wow. But if you've been thinking about it and looking at it closely, you can see that actually the PocketQube has been enhanced. It's probably about 10x the actual size there. All right. Okay, here we are. What is SpaceX all about? Now, obviously, everybody here, this may be remedial. In fact, I've been out of university so long, this may actually be coursework at the moment for introductory aerospace folks. But okay. So I'm gonna pick a little bit on air and space here. That's not to call them out or anything. I could have put Roscosmos there. I could have put ULA there. It's the same story. What we've seen for years and years and years. In this case, 20 years worth here with the I get this to work. About 6 launches per year to fulfill a baseline demand. So you have governmental customers, extremely high value payloads. You need to fly, you need to do it right. You can't have any mistakes. And so the industry that has sprung up over 50 years has supported that, right? So six roughly launches per year. It's not pushing an envelope. It's not going above and beyond that baseline demand. You get a high quality product, but you also have limited to no investment in production improvements to the rate of production. There's no incentive. There's a little bit of incentive at booster recovery in the example of Air and Space, but it's only for research purposes or analysis, that sort of thing. Nothing that's going to lead to reflying boosters in any material way. And failures are going to happen infrequently. Well, that's great, right? But at the same time, because you're not failing often, it means you are not used to the practice of failing. So when you fail and you have to shut down, it's going to be a really long pause. It's going to be a real long time before you get back to flight. Again, the pressures of this are not inductive to improving iteration, improving analysis, improving cycles, and improvement processes. So again, launch costs stay high. Now we're going to look a little bit at SpaceX here. SpaceX has a philosophy of increasing the launch rate to induce new demand. So this is sort of a thing that's been fundamental to SpaceX. Is they're going to open up new markets by reducing the cost to space, and they're going to do that by flying more and more and more and more. And that's going to induce new demand. New people are going to become aware that this is an option that they can fly to space. We are taking advantage of that as PocketQube developers. Fly more often, you're going to have more failures. You're going to be pushing the envelope. You're going to be understanding your process more, and you're not always going to get it right. And so you're going to have more failures happen. And because you have more failures, you're going to be able to have a process in place to address them and come back and understand how to move past that and come up with mitigation and come up with redesigns and things that can do that. The more often you fly, the more product you make, you can reduce supply chain costs. This is why traditionally in the automotive industry, the cost of a car has come down greatly. You look at the Model T as an example. You build a lot of something. You can buy a lot of wheels. You can buy a lot of car doors. You can, everything you're buying more of. You're pushing that supply chain down. You're forcing those manufacturers to supply into you to make more improvements, to make more product, to understand their product better. More chances to try out improvements, including recovery systems and logistics. People from the outside may not completely appreciate how often a rocket at SpaceX is changing. Like literally, practically every rocket that goes up has something different. It's not, oh, wow, it's Block 5. Well, Block 5 was a big change, is a huge change, and we're going to see that here in a little bit. But every single rocket has at least something different. And to be honest, this is basically the same with Unicorn. We have that same philosophy where we're going to iterate and we're going to change things and we're going to push that boundary. Not everything is going to be what we consider a major change. Some things are going to be a minor tweak here and there. Certainly the software is, you're just going to refine it over and over again. But every time you fly, gives you another opportunity to try out a new enhancement. And the more factory flow you get, the more that you're becoming that automotive assembly line mentality, the more that you can understand how long it takes to do each step, break it up into different stations or different work elements, have different people specialize in certain things, be able to move product through the factory faster without getting blocked. And again, over here, we've got a comparison. Wow, this is great right here. This is Block 5 right in here. Keep that in mind. 2019, that's going to be important. We're going to come back to that later. This is launches, right? This is valuable to us because it knows how many opportunities we have to fly. And this point in here, 2019, that's a pivot point. That's where we get Block 5. That's where we get this incredible rate of, now granted, a lot of that's going to satellites' own internal consumption, or SpaceX's internal consumption of satellites. So we don't have that pushing down costs necessarily. There's not demand to fill all that external to SpaceX. But at the same time, that is launches. That's incredible rate of launches there. But what's more important in my mind is reflight here. So here's 2019 again. What did we see? Let's go back. Oops, I'm all over the place. This is launches are taking off. Huge amounts of launches. This is booster production. This is time here. And these are booster serial numbers. Up until Block 5, we're launching, occasionally recovering, maybe reflying once, learning how to do reflight. It's only here until you get to 2019 with the big Block 5 enhancements for reflight. Every single one of these, look at all these colors. This is one booster, refly, 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 refly. That's one booster all the way across there. And the slope, this is what gets it right here. Look at this, time, serial number. This is a particular rate of production. The steeper the slope, the more boosters you're making per year. 2019, when we see a huge increase in launches, we see a corresponding decrease in booster production. Is that crazy? How many people knew that before this? A few people. So what effectively happened is we're no longer throwing an airplane away every time we launch a rocket. The first stage booster, stage 1 for Falcon 9, is essentially an airplane. You know, you got engines, you got an airframe, you got control systems, you got electronics, avionics, everything in here. It's essentially an airplane. Up until recovery and reflight, whenever you launch a rocket, you're throwing an airplane away. And this, I'm sure that Elon has mentioned this before. I'm sure I stole it from him. But I love this analogy here. This is basically an airplane that we're no longer binning after every flight. That's what's driven the cost down. The fact that we no longer need to make all those aircraft or airplanes or boosters in this case. Let's see. Okay, this is my opinion here. The success of booster recovery that unlocks booster reflight, there's sort of 3 things in my mind that unlock that. And this is where we start to get into how is this applicable to PocketQubes, right? This is the thing we really care. First is a dedication to working the problem. Back when I was at SpaceX here in the 2012 to 2019 range, we did not know that this was going to happen. This was not a foregone conclusion. This was essentially unknown at this point. We'd get a few back. We know we couldn't refly them. We'd have to do a lot of research and figuring out what learning we could get from that in order to change the way that the landing strips would work, or the grid fins, or who knows what. You know, all these engineering efforts to change the design with no guaranteed payback, burning a lot of man hours to try and solve a problem that we did not know could be solved. I'm going back. And again, there we go. So that dedication to working the problem, having a great team of people that can work a problem, try and solve those hard engineering questions, try and come up with solutions to them, and come up with a mitigation that can make it reliable, all these sort of things that go into it. That right there, this room, the folks in this room, you have that skill. You have that equal to SpaceX. I'm proud to say, from what I've seen at Alba and from all of you, that's equal to what they have at SpaceX. There's no question about that in my mind. So you have that. This one, maybe not. However, as we continue to go into this, we're going to go through these slides here. I think that we're in a great position as a PocketQube community to be able to say, yeah, money, yeah, you have to worry about money. I can't lie about that. But what happens is, by flying as low cost as you can, it gives you more opportunities to iterate and improve your process. And of course, this is a callback to the launch slide. This is PocketQubes. Again, this is cumulative, but you know, you can start to see there's a beginning here in PocketQubes of where SpaceX was, you know, maybe 10 years ago. Okay, so here's what it comes down to. Some people will say, or at least in America where I'm from, there's a big focus on CubeSats being the low-cost solution. If you talk to people in America, there's not a huge awareness or understanding of PocketQubes. Unfortunate. Yes, hopefully we can change that. Because PocketQubes are, we've got here 3 opportunities. This is representative. I don't have actual numbers in here. But let's say, for example, we've got 3 opportunities versus a CubeSat, you've got 1 chance. If you have enough money to fly a CubeSat, you go do an investment round, you get enough money, you get enough design skill, you got people working on a CubeSat, you have a great payload, you have a great idea, you think you can pull it all off. Something very simple, you know, we have a long, complicated path to take from start to finish in order to pull off a launch to get a payload in orbit and operating. It doesn't matter the size of your satellite. You have to walk that path regardless of what you're doing. With a CubeSat, if you have enough money to fly a CubeSat, great. You can show that off to investors. You can show that you can fly a bigger payload. You can say, wow, this is amazing. That's an awesome idea. But if you get enough money for 1 CubeSat and something goes wrong, of the hundreds of thousands of different steps that need to go along there, you're done. You're out of luck. You spent all of your engineering effort and your work and everything. You're now in a point where you have to go back and try to go back to the same people, go back to new people and say, well, okay, we failed, but we can do better this time. That's a real hard sell. With PocketQubes, if you can fit your payload onto a PocketQube, so that's the caveat, right? If you can fit your payload onto a PocketQube, you want to go as small as you can, because it doesn't mean that you're going cheap. It means that you're being efficient with your money. You're flying as many times as you can. You can hang on to those engineering resources, that skill set that you're developing over time, and you can iterate. You can keep going. This is part of the core principle of Alba, where we know that not everything is going to go right the first time. We know that rocket launches do blow up. We know that, you know, a sensor will have a failure and we will be unable to get data from it. We know that those things can happen. The more often that you fly, the more that you can mitigate that, you can gain heritage, you can learn from it. Size your subsystems to your payload. So if your payload is so big, don't go overboard. You know, you want to look at shrinking everything down as small as you can. And of course, that's been the narrative of most of the talks here as well. People coming in with awesome, great ideas on how to make a small subsystem or small accessories that can go along with your PocketQube to be able to enable it to fly its mission. Again, whoops. You have a lot of money, you can fly a big flashy satellite, but you have to get it right. If you fly a smaller one, it'll still look pretty cool. It's going to be a great shot at getting right. If it doesn't, you can do it again. You know, so we've been talking about cost, complexity. Takes longer to integrate, to iterate. ADCS propulsion, power systems. You know, you consume more power, you need more solar wings. You consume more. You have more mass, you need more ADCS. It's a compound factor, right? We all know this. Smaller size, you can be scrappy and innovate. You can build custom subsystems yourself, hopefully with smaller costs. Because even if you don't get it right, even if you are sort of holding it together with bubblegum and paper clips, it's going to give you that proof of concept and allow you to iterate, to design robustness into it, but knowing where to enhance. Okay, this is just sort of a throwaway slide here. Many of you already know this, but even if you're not going to fly something right off the shelf, you can what we have with cell phones, Hobby RC, drone products, all this sort of crazy stuff that's on the market that comes out every year. We've got tons of sensors, tons of mechanicals, tons of accessories and things that can go along with it that you can just throw on your proof of concept to get yourself going. If you're not an expert in one system or another, there's tons of YouTube videos out there to learn how to do it. I think everybody in this room, again, knows how to sort of, be scrappy. That's like one of the core concepts of SpaceX, right? Is be scrappy. make do with what you have, figure out a way to make it work. And then, of course, the question is, well, okay, what about reliability? SpaceX had no reliability. They had no flight heritage when they started, right? Well, nobody does. Yeah, you can buy it. You can go out there into the marketplace and buy a proven CubeSat design that has a ton of heritage behind it. You're spending a lot of money for that reliability. Again, okay, that's great. Maybe that one subsystem is going to be perfect for you, and you don't have to spend time designing it yourself and figuring out a project managing how to get that into your satellite. Uh, but let's say the harness that goes on that subsystem is something you didn't put a lot of time into, and you have a short or disconnect or something, and then you lose that whole ability to use it. So it's this network, thousands of steps, like I was saying. Everywhere is an opportunity to trip you up. If you go cheap, you can fly often. The more often you fly, the more likely you are to get flight heritage. Yeah, shrinking your subsystems becomes an advantage because you streamline and customize your requirements and test procedures to your payload needs. Again, if let's say you buy 10 different subsystems for a small sat, then you have a lot of people who have to sit down and read all the technical design documents that go with those subsystems in order to integrate them all together. That's just more and more, even if you're outsourcing that risk of and trying to burn down your risk by buying heritage, then your integration becomes more difficult because you're unfamiliar with the subsystem you just bought, and you have to try and integrate it with all these other subsystems. Doing it yourself, it can have a longer lead time, right? Potentially, but you're burning down that risk. You have a better chance of catching those failure modes that are unique to your use cases because you're learning it as you go. Okay, here's some examples, the good stuff. First, we're going to look at backplane. This is our largest PCB. We have several PCBs on the Unicorn. You can see them downstairs on our model. This is the largest PCB. It does most of the processing work. Basically, all of the computing runs through here. We've had a number here. We've got 1, 2, 3, 4, 5 different iterations on the screen here. We've been able to iterate it by flying. Every time we fly, if we have a respin, or even if it's just a couple component changes or things like that, it gives us an opportunity to learn from it, learn in flight what kind of data we get back, where do we see there might be a problem or something we need to beef up. We add a new subsystem, we add new enhancements, we can change the backplane, respin it. It's relatively low cost. We get new flight heritage, a new product. By moving through the evolution here, and again, actually, this is great. I love this idea where we are changing the color of the mask every time we fly. It's sort of a visual reminder what we've learned. But okay, so some of the things we've done as we've moved through our life cycle here as our design process. We've reduced our power consumption. We've improved the transfer rate of data between different processors and radios. We've improved the thermal performance. Tom loves to talk about that. Ask him about him later if you want to learn about that. We can catch and eliminate unexpected failure modes. The more you build, the more you handle your product, the more opportunities you have to drop it on the floor or dip it in water. So these are the sorts of failure modes that you can learn from. Improving reliability of harness connections. I talked about that. This is one thing that I want to dig into more that I think the PocketQube community can really benefit from. Is there's an inherent, because we're in a small form factor and we're at risk of the cold temperatures of space, harnessing can be a big risk. I think we tend to overlook this. Taking advantage of newer versions of integrated circuits. We've been designing this for several years now, and it's amazing. You look at what's coming out of the design labs for 𝗖cies, and it's just crazy the kind of things you can buy now that you couldn't buy even like 3 or 4 years ago. There's new versions of things, things that are modules now that would have previously been an entire board or something. We can really take advantage of that in the PocketQube community. 𝗖cie, Stuart had a great talk yesterday. A lot of good stuff on that. And this is crazy because we're running so many unicorns in space, so many reaction wheels. We have something like over 50 rods and 50 wheels that we've flown that we have data on now. And we can learn from it. Here we've got an earlier iteration with a different mass profile here. This is what we're currently flying here, this version. Because we have all that data, we have all this performance and test data from our lab. We've been able to improve both the design and the manufacturing process. We get lots of opportunities to test this as we're building it. Reaction wheel speeds and responsiveness are very repeatable and reproducible. This is something we used to have a little bit of problem with. We're doing much better there. Our in-house magnetometer winding process, we've sort of dialed that in a little bit further. That's something you'll be able to see the machine tomorrow as well. ADCS structures. Here's our original aluminum. Right now we're on a composite. We're moving to our initial composite solution did have conductive element to it, and we've been able to engineer that out of it. So we've got a non-conductive composite. So again, multiple opportunities to iterate there. Reducing mass, complexity, cost in our structures. The more we fly and we test and we shake and we work with these, you figure out where you can cut corners on the mass of the structure. What can you reduce it from 5 contact points to 3, stuff like that. Fast 3D printing, eliminating tool costs. This is stuff. This is not new. Everybody here should kind of have an awareness of what PocketQube form factor can do. Attachment points, yes. Okay. Some people have alluded to this or put up some slides here already on this sort of the value. This is what we call value stream in automotive manufacturing. Being able to go back to my original challenge of increasing production rates, we have to be aware of what the entire value stream looks like. What are the steps that it takes from design all the way through flight? How much time does it take to do this? What sort of resources does it take? What sort of skill sets of the people that are doing the work? What sort of capital equipment do you need? Or could benefit from if you don't have it already? There's certain automation things that could happen that are not terribly expensive that could be starting to look at. And granted, this isn't particularly applicable if you're only going to fly 1 or 2 satellites, but this is something to keep in mind because depending on what your payload is or what the application of the customer might be, there's always that viewpoint that you need to think about scalability. Ultimately, even if you don't have that in the forefront of your mind, that payload may lead down a path that's going to be, let's make 10, 20, 100, 1,000. So procurement, being able to buy at the right quantities at the right time. Again, taking advantage of perhaps minimum order quantities or bulk buy discounts if you're going to fly a lot of product. It's great. Subsystem build. As we saw in some of the earlier slides, being able to take advantage of those iterations, how many times you do a redesign, will give you the knowledge of how that process runs, be able to come up with redesigns for manufacturability. Flat sat, we're going to talk about that just here we got the slide here. We had a couple of people already talk about this a lot. This is a great concept here. If you haven't sort of run across this before, this is very, very common at SpaceX. Largely at SpaceX, we call that HIDL or hardware in the loop, where you're running flight software on flight hardware or compatible. This gives you the opportunity to understand how your system works as a whole before you put it all together. And it also gives you the opportunity to swap a new product in. So say you've got everything here, let's say is flight, and you want to fly a different sun sensor board. You can swap that in, and it's just like, and you can run the software and spin it up and see how it works with a new board, just like that. You don't have to think about how you're going to do it. It does require the investment of having sort of products sitting there waiting to test. If you aren't yet to the point where you're going to fly. But once you get to the point where you're flying, you got all your flight hardware right here, you run your software, and it's like you're done. And then you've done that without having to build the full package up and risk having to tear it down and build it up, tear it down, that sort of thing. After flat set, after your checkouts, after your software works good, all of your function tests work good, you build it up into assembly. You do any assembly tests, deployments, that sort of thing you're going to do, integrate to your deployer. That's a value stream. This is how you visualize it in automotive, and you want to say, okay, every step along the way, we have to understand the bounds and the time that's required and the spin that you're going to need to get through that step. What's next? Okay. If you haven't already signed up for a tour slot for tomorrow for our factory in Hillington, it's only 2 short train rides away. I got to say, the public transit here is great. I'm coming from LA, so I don't know if that's saying much. You'll be able to see our build and test process. All the folks in red shirts here will be there to help show you through what we do to build a unicorn and an Alba pod. There's a lot of cool stuff. Right now, or I would say, based on what I've done so far, understanding the build, it takes a while to get into this, understand what's going on. I haven't quite been with Alba for a year yet, but right now we're at about a capacity of 9 unicorns a year. We're not actually building that, but we could meet that without any sort of further investment, improvements. Really, we have the capacity in place to do that. 3 campaigns of 3 unicorns each. We're starting to make a few improvements in the process. We're starting to understand what that end picture on design looks like. We've talked between Stuart and Tom, we've talked a little bit about some of the future things we're adding in. We're getting to the point where we're almost mature enough that our future iterations will just be sort of polishing minor changes. We're almost to the point where we're at a stable initial start of our end product, if that makes sense. As we design that, get those design parameters in place, we're looking on the throughput enhancements. That's the piece that I'm really looking at. I have a strong confidence level that we can hit about 18 unicorns per year by the end of the year. Will we be building that at that point? No, we won't quite be building them at that point, but we could potentially. We could, and then I don't think it would be a huge stretch to be able to build 50 of these things within a couple, 2-3 years, which is kind of a crazy level when you think about it, right? That's a lot of PocketQubes. And sort of for conclusion here, I want to say that cost is a main driver for selecting the form factor, right? We all know that. That's probably for 80% of the folks here, that's the reason you're in this space, is knowing that it's a low cost entry, that you can move quickly and to get the funding, you can move quickly to fly and get into space. But I don't think it's sort of a trap to think that the story of PocketQubes is flying a cheap satellite. That's not really the use case here. The true benefit of a PocketQube is being able to design your satellite as small as you can, that you're both maximizing the number of design iterations and build events and test campaigns and flights that you can afford, and you're also being able to do it efficiently with the skills that you're able to tap into. Right? So I'll also throw this up here as sort of a last look. Even SpaceX at this point, with all the capacity that they have, that they can throw at it, they're packing these in as tight as they can, right? They've designed Starlink satellites to be able to be folded flat like this in an extremely tight form factor. Obviously, this is bigger than a PocketQube, but I mean, like, look at how many they have in there, and I just can't, it's crazy. So thank you very much. I'm glad you sort of were able to hang in there with me. I probably went a little short. I knew I would, unless I did. But thank you. I will be around for questions.